Okay, hi. So in today's video, we're going to be discussing surfaces of revolution. We've been seeing these solids obtained by taking functions and revolving them about axes to get different solids. We've been finding volumes of them. Now we're going to look at surface areas. So if you haven't seen the volume videos, I encourage you watching them. In addition, if you haven't watched the arc length video, I encourage you to watch that because the formula for this will rely on the arc length formula. Let's get into it. So we can apply what we learned about arc lengths to surfaces obtained by revolution to compute the surface area of such a solid. So let's zoom in here to our horizontal axis of revolution. Our formula is surface area equals 2 pi integral from a to b of r of x times square root of 1 plus f prime of x squared dx. So the explanation for this formula might be a bit confusing, but you can see the essence of some things in here. Like we see 2 pi r, which reminds us of the circumference of a circle, which is good because we're evolving something about an axis and its cross sections are circles. We also see this here, which might be a bit familiar to you. But let's try to see what's going on here. So let's take this function in the picture here, and it's being revolved about this x-axis. So let's try to draw what it looks like. It should look something like this. It's like a lamp or something. So the idea is similar to what we did for volumes. We're going to take these small cross-sections, and instead of finding the volumes of them, we're going to find the lateral surface areas of them. So this time, you'll note that this part here, the square root, is the arc length formula. That's what we used before with this integral here. So we rely on arc length, which was a derivative, not like the mathematical derivative, but it followed from the distance formula. And remember, the distance formula was based off of the Pythagorean theorem, where we got the hypotenuse of the triangle formed by 2 points along your curve. So now, instead of these disks, where before we had something like this, if we were to find the lateral surface area of that, that's not good enough, because the actual part of the curve that we're looking at is this right here. And the lateral surface area of that band is considerably different than the red lateral surface area. So instead of using a disk, we have to be a little bit more creative and just curve our ends. So now we're using basically a frustum cross-section. It's part of a cone, and we have to find the surface area of that. So if we call the length of that little slant like delta L or something, that's the length of that little slant, and suppose we're also given the middle line here, and we'll go to the center where this is the axis of rotation, and if that length is r, then we can compute the lateral surface area of this frustum by using 2 pi r times delta L. And you can imagine we'll try to make that delta L really, really small, and for that, delta L is arc length, so that's how we plug this in our formula for arc length there. There's a little bit more derivation you can do. You can call this dl, use our formula for arc length, and eventually you'll receive something like this. So that's the derivation of this formula. That's what we're going to be using. And then for a vertical axis of revolution, basically identical, just now we have functions of y. So we'll be doing similar things as we did with volumes, where sometimes we had to do a change of variables. We'll have to do that if we revolve around a vertical axis. Let's try to do some practice problems. Find the area of the surface of revolution formed by revolving the graph of f of x equals x cubed on the interval 0 to 1 about the x-axis. So let's try graphing this really quickly. We'll just look at the first quadrant. We have the function f of x equals x cubed, which looks something like that. And we're only going up to 1 on the x-axis. So our region that we're looking at is this red region. We're revolving it about the x-axis. So the final shape will look Oh, let's see if I can draw this. Something like this. And we're trying to find this lateral surface area. It's like a cone, but its edges are concave or something like that. So that's what we're trying to find, and for that we'll use our formula. We're using a horizontal axis of rotation, so it's going to be v equals 2 pi integral from a to b r of x times square root of 1 plus f prime of x squared times dx. We're given f of x, so we can compute f prime of x just by taking the derivative, 3x squared. That's great. We know our bounds of integration because we're integrating with respect to x, and the bounds were given from 0 to 1. So a equals 0, b equals 1. All that remains is to find the radius. And remember, the radius, if we were to draw one of our little frustums here, the radius was the distance from the axis of rotation to the function at the middle point. So in that case, it would be here, which is the function value at our value of x, right? That's what we're looking at. So it's the function value, which in this case is just x cubed. So with that, we can plug it into our formula. V equals 2 pi integral from 0 to 1. R of x, we just said, is whatever it's on the function, so it's x cubed, times square root of 1 plus 3x squared squared dx, right? So maybe this is a little bit confusing that the radius is in the middle of them, but remember our width is so small that for that value of x, we can just take the function value, and that's going to give us the radius there. And this all comes from that lateral surface area of a frustum, 2 pi r times that tiny width. And now it's just about solving this integral here. So we can solve this. This is 2 pi 0 to 1 x cubed times 1 plus 9x to the 4th dx. Let's use some u substitution. U is equal to 1 plus 9x to the 4th. du is equal to 36x cubed dx. So this will equal 2 pi integral x cubed times u to the 1/2 times 1 over 36x cubed, or sorry, du over 36x cubed. We do some cancellation, and we get, let's see, pi over 18 times the integral of u to the 1/2 du. That's equal to pi over 18 times 2/3 u to the 3/2. And then we can substitute back in for u. So this is pi over 27 times 1 plus 9x to the 4th to the 3/2, evaluated from x equals 1 down to 0, and then do our plugging in and subtracting, and we get pi over 27 times 10 to the 3/2 minus 1 to the 3/2, which is approximately equal to 3.563. So again, very formulaic with how we're doing things, but again, it's just obtaining the correct values. So in this case, you can see that the hard thing to obtain will be our r of x value, but that just follows from how we did volumes. It's the same idea of finding that r. Let's do another problem. Find the area of the surface of revolution formed by revolving the graph of f of x equals x squared on the interval 0 to square root of 2 about the y-axis. So let's graph this quickly, and we'll graph x squared, looks something like that, up to the square root of 2. And I guess I should have said that it's also bounded by like the y-axis. So like the area that's being revolved is this black region here. I'm actually going to use a different color. It's this red region here. We're revolving this about the y-axis. Okay, so It's a vertical axis of rotation, so it's going to be the other formula, v equals 2 pi integral a to b, r of y times square root of 1 plus f prime of y squared dy, right? If we scroll back, that's the equation right here. It actually uses g prime, but too bad. Okay, so now it's a little bit of an extra step where we have to solve for y, but that should not be too bad. So we can let y equal x squared, because that's what we're given. And that means x is equal to plus or minus the square root of y, but since we're looking in the first quadrant, it's going to be x equals the square root of y, which I'll call 1/2, or sorry, y to the 1/2. Okay, so that's what we're dealing with here. Now we have to find the radius, so for that we can draw our little shape here. And the radius is going to be that distance, because remember, that's only half of the actual circle. It gets revolved around the entire y-axis. So if this point here is x comma y, given a value of y, we can obtain our radius by looking at the x-coordinate. The radius equals x. So given a value of y, we can obtain the value of x. For that, we can use the equation x equals the square root of y. So that means r of y is going to be equal to the square root of y. We also need f prime of y. So for that, we'll take the derivative of the square root of y, which is why I wrote it as this. So 1/2 y to the negative 1/2. Now we're ready to plug in and integrate. V equals 2 pi integral. What are our bounds of integration? With respect to y, we start at 0, and then we go up to this point, square root of 2 comma 2, because we plug it into f of x equals x squared. Square root of 2 squared is 2, so our upper bound will be 2. That's the y value. R of y is the square root of y, and then we're multiplying that with the square root of 1 plus 1/2 y to the negative 1/2 squared dy. Let's try to simplify this a bit. 2 pi 0 to 2 square root of y times square root of 1 plus 1 over 4y, right? 1/2 squared is 1/4, y to the negative 1/2 squared is y to the negative 1. We can combine those into 1 over 4y. From there, this might be a little bit hard to integrate at first, but we actually can integrate this. Let's combine these into one square root. 2 pi 0 to 2 integral, or square root of y plus 1 over 4. And from here, maybe you're feeling a bit more confident. We can do some u substitution. U equals y plus 1/4, du equals dy. We're left with 2 pi integral square root of u times du. We can integrate this. This is 2 pi times 2/3 u to the 3/2, which is equal to 4 pi over 3. U is equal to y plus 1 over 4 to the 3/2. We're evaluating this from 2 down to 0. And in fact, you don't even need a calculator for this. You can do this with your brain and your hand, so let's do that. This is 4 pi over 3 times 2 plus 1/4 is 9/4 to the 3/2, and then we'll subtract 0 plus 1/4 is 1/4 to the 3/2. 4 pi over 3. 9 over 4 to the 3/2 is equal to the square root of 9/4 raised to the 3rd power. The square root of 9/4 is 3/2. 3/2 squared is 27, or 3/2 cubed is 27 over 8. 1/4, the square root of 1/4 is 1/2. 1/2 cubed is 1/8. So this is equal to 4 pi over 3 times 26 over 8. This you can simplify a bit more. 13 pi over 3. So a bit of integration and algebra practice right there. But there you go, that's the surface area. Again, it's It's all about putting it into the formula, but making sure you have the right value of r. Don't be afraid if your r value is very similar to your f of x value. We saw in the volumes video that the radius was often equal to that function value. So it's a very similar thing here, just a different formula. One more question. What's the absolute value of the difference between the volume and surface area of the solid obtained by revolving y equals sine of x on the interval 0 to pi about the x-axis? So you're probably like, oh gosh, now I have to do two things, volume and surface area. It's not that bad, trust me. So let's draw our coordinate axes here, only the first quadrant. And if we were to graph sine of x, we would get something that looks like this. Pretty boring. 0 to pi, and we're revolving this. Let me color in the region. We're revolving this about the x-axis. So horizontal axis of revolution, we have to remember two formulas since we're doing volume and surface area. Volume is equal to pi times the integral from a to b of r of x squared dx. Surface area equals 2 pi integral a to b r of x times square root 1 plus f prime of x squared dx. Surface area formula is just a little bit more annoying, so let's do the volume formula first. We can solve this by using one of our methods. We can use the disk method, we can use the washer method, we could use the shell method. For this, I feel like using the disk method. Why? Because our region is touching the axis of rotation. I can draw my little radius here or my little disk here, and we can figure out the radius pretty easily, right? Given this value of x, I can tell you that this point on the function is equal to xy, so my radius is going to be equal to y, and that holds for any x value that I choose. Like x1, y1, our radius here will be equal to y1. We know that y is equal to f of x, which is equal to sine of x. So that means the radius is sine of x. This is just a review of our disk method video. So now we can solve our volume. Volume equals pi. Our bounds go from 0 to pi. R of x is sine of x squared dx. And for this, this is actually a hard integral to solve by hand, and I don't think we have the ability to with what we've learned thus far. But maybe you are able to solve this. If so, go for it. You can just plug this into a calculator for now, and I believe this is 4.935. So that's our volume. Now let's do surface area. Let me move the volume off to the side. Okay. Surface area, we should already be able to basically solve it. The radius is going to be the same thing. We're using similar disks, it's just now we're doing those frustums, but the essence of those disks remain the same. The radius will be the same. It's still going to be sine of x. F of x is sine of x, so if f of x equals sine of x, then f prime of x equals cosine of x. And we're ready to solve. 2 pi integral 0 to pi of sine of x times square root of 1 plus cosine squared of x dx. Okay, now it's about solving this. For this, you can try to solve it by hand if you know some of the more advanced integration techniques, or you can just use a calculator. If we use a calculator, we get 14.424. We're asked to find the difference, the absolute value of the difference. So we can do that, and we get 4.935 minus 14.424. The absolute value is about 9.49. Just a fun little problem to end it off, but the point was to review volumes and see how similar the computation of volumes and surface area are to each other. The formulas are a tad different, but notice how the radius is basically identical in this example. We just also have to add in that arc length piece, 2 pi r, things like that. But notice the similarities. So hopefully you're already feeling like a master at this because you've done so much practice with volumes. And that actually concludes this section of this lesson. So hope this was educational. As always, leave some comments below if you have any questions. And yeah, I will catch you in the next video. As always, take care.